Thank you. So here we go again. Today my talk is going to be organized in these 4 parts. Let's talk about the motivation first. So the idea of sum-free function comes from the APN function, which is almost perfect nonlinear function, and it is a very important in symmetric cryptography, especially in the block ciphers. And how does APN function define? Is using the differential uniformity, which is a delta f, is defined to be the maximum of the equation of the difference of fx plus a minus fx equal to b, where a is a non-zero element in fq and b is an element in fq. And we take the maximum of the root sets. Oh, sorry. Oh, sure. So do you hear me? Okay. So the differential uniformity is defined to be the maximum size of the root set of such equation here, fx plus a equal to minus fx equal to b, where a is a non-zero element in fq. And once we see that when the differential uniformity equal to 2 for the function f, then the function is said to be almost perfect nonlinear. And we know that the multiplicative inverse function, x inverse, sending every element in fq to x inverse and sending 0 to 0 is sum-free. It's APN for when the n is odd. And from here, Claude-Cayley come up with the idea about sum-free function to be a generalization of APN functions. And in particular, the APN function is exactly second-order sum-free. And so how does sum-free function defined? It's like this. So when we take, we say that sum-free function is always for kth order sum-free, and k is a number from 1 to n minus 1. And we take a k-dimensional subspace A of the FQ, and then we sum up all the function values over this subspace, and we say that when the sum is non-zero, we say the function is sum-free function. So we say the function is not sum-free when the sum is 0. And we call, and Claude-Cayley gives that for the A to be an affine subspace not containing 0, then the sum is always not 0. And there's some interesting facts like F inverse is trivially first order sum-free, and F inverse is second order sum-free if and only if n is odd. So recall that the second order sum-free is exactly APN. And then Cayley gave this conjecture that for n greater or equal to 6 and k is from 3 to n minus 3, the multiplicative inverse function f inverse is always kth order sum-free. And equivalently, this is to say that for every k from 3 to n minus 3, we could always find a subspace E such that the function value sum to 0 over this space E. Sorry for that. And from now, this is notation. So from now on, we always assume k is from n is greater than 2 and k is from 1 to n minus 1. And we define Sfn to be the other case such that f is sum-free on f2 to the n. And we define kn to be other case such that f is not kth order sum-free. And so the Cayley's conjecture just saying that for n greater or equal to 6, 3 to n minus 3 is a subset of k of n. And here is some, so the sum freedom is studied in in last year very well. And here's some very previous results, like when k and n is not a coprime, we say that k is in kn. And also we have the duality for the sum freedom. When k is in kn, then n minus k is in kn. And when k is in Sfn, n minus k is also always in Sfn. And also we have that for even n, the conjecture is done. For even n, the Sfn is exactly n1 and n minus 1. But for odd n, we don't know yet. But we know that 1, 2, and n minus 2, n minus 1 is in Sfn. And the conjecture is confirmed for several types of n's, like when n is less or equal to 27, and when n is divisible by 2, 3, or 5, the conjecture is true. And when 7 divides n, but with possible exceptions like 4923 and 4926, the conjecture is true. So the conjecture is quite like relatively hard when the n is a prime power. And also for the if we take L to be the smallest prime divisor of n, such that L minus 1 satisfies this equation here, and then the conjecture is also true. And here we have more. So if we know that the polynomial xn minus 1 has a factor like this way, the coefficient for x term is 0, then the function is not k-order sum free. So, but note that here the factor don't need to be irreducible. It's just a factor. And also, when have that when k is greater than 3 and n satisfies this inequality, then k is in K of n also. And if we have KL to be 2 elements in K of n, and the KL, the product of KL is smaller than n, then the K plus L is also there. And also we have that for this range of K from 3 to the minimal 12, n minus 3, K is also in K of n. And also when K, sorry for that, when K is in the first, like almost the first third of the range, or the last third of the range, then K is in Kn. And also, we have 2 criteria to determine the existence of zero-sum subspaces. First, let's recall, they rely on two irreducibles. So let's recall the construction of such irreducibles. First, we will use a Moore determinant, which is the determinant of in k variables of x1 to xk, and using all the conjugate of them. And the delta is the Moore determinant, but delta 1 is we drop the ith line of the Moore determinant, and we add 1 line at the bottom. And we could verify that delta will always divide delta I for I from 1 to k. So we could define the polynomial using delta 1 divided by delta. It will be a polynomial in F2, but in variable of k variables. And so we have the criteria saying that for k-dimensional subspace E, and how do we know it is zero-sum subspace? We just take all the roots of E and evaluate of the function fk at all the roots. And so E is zero-sum subspace if and only if this function, this polynomial value is 0. And here's some fact about the polynomial fk. The degree of fk is always 2 to the k minus 2, and degree of fk in variable xi is 2 to the k minus 1. And also for k greater or equal to 3, the polynomial fk is always absolutely irreducible over f2, f2 bar, which means it is irreducible over the algebraic closure of f2. Okay, that's good. So now let's go to another criteria. So for now, we denote Vk of f2 to the n to be the set of all the k-dimensional subspaces. And we take E to be one of them. And we take the subspace polynomial to be the product of all the x minus u's for u in E. And this is actually a 2 linearized polynomial. So means it will be a F2 linear map from F2 to the n to itself. And the kernel of LE will be E itself, and the image of LE has dimension n minus k. And now we denote the image of LE to be E prime, and then we will have a fact that E double prime will be E itself. And we could define the trace dual space to be E orthogonal, like to be all the elements sending that the trace of the product xy is equal to 0 for all the y's. And then we could have a bijection is from all the k-dimensional subspaces to all the n minus k-dimensional subspaces, sending E to E prime orthogonal. And keeping this in mind, let's talk about some other things like so if we have an integer and we take the two-edit partition, it is called the partition such that all the part is for power of 2. So, and we denote Rk to be the two-edit partition of the number 2 to the k minus 1. So for example, oh, sorry for that. So for example, if we take k to be 4, then Rk is equal to, we showed here, like 2 to the 3, 2 power 2 square, like this. And also we define the monomial m lambda. So we take lambda to be a two-edit partition of 2 to the k, and we take lambda to be one of it. And then we define the polynomial m related to lambda to be like this. So if you have lambda has size j, then we take j variables and take the power of the element in lambda. So for example, for 2 to the 3, we define m2 to the 3 like this. We take every time we take one variable, and for m2 to the 2, we take every time we take two variables and evaluate them. And then we could define our polynomials, theta k to be the sum of all the lambda k's, where k is a partition of the 2 to the k minus 1. And this polynomial, it is also a polynomial in F2, and has k variables. And this polynomial is essential in determining the zero-sum subspace. So similarly, we have that if you have E to be a k-dimensional subspace, and we take V1 to Vk to be the basis of E prime orthogonal, then E is a zero-sum subspace if and only if theta k valued at V1 to Vk is 0. So remember that we have a bijection from E to E prime orthogonal. And we know that for k greater or equal to 3, the theta k is also absolutely irreducible over F2 to the bar. And the degree of theta k is 2 to the k minus 1, and degree xk of theta k is 2 to the k minus 1. So degree theta k here is smaller than fk, making it more powerful when we use a long-well bound to determine all the roots of it. Here is an example to show you that these two criteria, they are essentially the same. So here we take n to be 17, and we use this irreducible f to generate all the elements in F2 to the 17, and we verify that. For if we take a subspace E has basis U1 to U5 given here, and then we could verify this is a zero-sum subspace by evaluating Fk at all the bases of it. And then we take the roots, all the bases of E prime orthogonal is given here, V1 to V5, and then we evaluate at theta k of it, it is also 0. Okay, so apart from those two criteria for zero-sum subspaces, we could also have a direct way to construct such subspace. So using this. As we said before, if a polynomial xn minus 1 has a factor like fk given here, the coefficient for x is 0, then we could construct a basis for zero-sum subspaces for dimension k, which is using all the conjugate of x for some x in the finite field fk to the n. And before I show you how we do it, let's call the Frobenius morphism to be sigma, which is the map sending x to x squared. And we will use a polynomial fk to show the existence. And this fk, it is 0 if and only if delta 1 is 0, but delta is not 0. And this is equivalent to say that all the conjugate of x are linearly independent over F2, but this set is linearly dependent over F2. So these two conditions and these two conditions, they are equivalent. So instead of showing this, you could show it here. Let's go. So here we will take alpha to be a normal element and construct the x using it. First, we write xn minus 1 to be composite with f and g. So f is a given before and g is the other factor. And we take x to be g of sigma evaluated at alpha. So because sigma is automorphism, right? So g of sigma is like another automorphism. We evaluate alpha, we got the x. And we could exactly show that x, or the conjugate of such x is linearly independent over F2. And also, this set is linearly dependent over F2, so making that all the conjugate this x to sigma square x to sigma kx will give you a basis of zero-sum subspace. Yeah. Yeah, so okay, the normal element is the element such that all the conjugate is a normal basis, right? So I think there should be some algorithm to determine that whether this element is normal or not, and you could use it. Okay, so any other question? Okay, so let's go. So we already showed that the previous result, two criteria, and the right way to construct the subspaces. Now let's see what's our contribution. We show that the conjecture is true whenever n is not a prime. So note that I mentioned before, right? When n is a prime power, it is rather hard to determine it. And now we show that for whenever n is not a prime, it is true. And our method is like a combination of all the tools in the algebraic and algebraic geometry. Like we will use the long wheel bound and Hess wheel bound on the roots of the irreducible polynomials. And our result will mainly count on an iterative method theorem. This theorem is given in last year's IEO program. So it says that when you have a R is in K of n, and you have a prime divisor L of n, and then we could actually enlarge the set from R to be a subset of K of n. It's given here. Okay. And also, we will use another polynomial fkl. It is like the expansion of fk. So we evaluate fk at u1 to it is still a polynomial in k variables, but it is dimension k plus l using u1 to ul to be some element in the finite field f2 to the n. And this polynomial depends not only on L, but U1 to UL also. U1 to UL determine its coefficient, right? And this polynomial has degree 2 to the k plus 1 minus 2 to the L. K plus L, sorry. Okay. And also we see that this polynomial fk plus L is also absolutely irreducible when we have U1 to UL is the basis of non-zero sum subspace. And also our result will count on an extension theorem. It is saying that because to construct zero-sum subspace could be rather difficult. So firstly, we found out that it is relatively easier to construct a non-zero-sum subspace, and then we could extend it to a zero-sum subspace. So let's start with U1 to UL to be k arbitrary linearly independent element in F2 to the n, and then we could actually enlarge it into L plus 1 element such that it is a basis for a non-zero sum subspace. And then after this, we apply the Hudson-Will bond about the absolute irreducible Fk plus L, FKL, then we could have that. Whenever, when you have U1 to UL to be basis of non-zero sum subspace, it always exists because of the previous theorem, right? And then if we have n satisfy this inequality, we could extend U1 to UL to be a basis of L plus one dimensional zero sum subspace. So here is the outline of our proof. So we start with the prime divisor n. We denote it by L, and we say that L is greater or equal to 7 because by previous results, when L is 2, 3, or 5, it's already done. And we could assume n is greater than 4L plus 7 because by previous results, when n is less than 27, it is done. And yeah. And then we take for each r from 3 to L plus 2, we take L prime to be r minus 2, and we could choose L prime linearly independent element from F2 to then. This could be easily done, and then we could extend them to L elements, L prime elements, such that they are basis for non-zero sum subspace. And then we could extend U1 to UL prime to U1 to UR such that they are basis for zero sum subspace using our extension theorem we showed before. And then using the iterative method, we could say that we could actually enlarge such R's to be a bigger subset of K of n. And if we take union of all the subsets on the left-hand side, we could see that actually they cover like the half of the range we want. And then by the duality, we could say that from 3 to n minus 3, they are all in the K of n this set. Any problem about the proof? Yeah, so till now we reach our conclusion that the Cayley's conjecture is true whenever n is not a prime. Yeah, but the problem is still opening because we don't know that when n is a prime, does it work or not? Because all our previous result is rely on the prime divisor L of n, but here when n is a prime, we cannot use the same method. And also, is there any more effective way to construct the zero sum subspace? It could be also an interesting direction. And here's the reference for our work, and you could see the third one, written by Balin, Ho, Riddle, and Zhao, is the work of last year's IEU. That's it. Thank you.